Okay, this is going to be take two, where we finish the section on unit circle definition for cosine and sine, and then we're going to, in the next video comes with the right triangle definition. All right, we're going to review the definition for cosine and sine from the unit circle. Remember, what we're looking at is we have an angle drawn. All right, it's drawn in red here, and we're looking for where the terminal side intersects the unit circle. If we draw a standard position with the initial side on the x-axis and the terminal side wherever it lands, then cosine of the angle theta is the x-coordinate, sine of the angle theta is the y-coordinate, tangent is the ratio of sine over cosine, or x over y. All right, so for us to be able to compute these cosine and sine values, we have to know the point on the unit circle for now. Right triangle definition will be equivalent. That's taken care of in the next video. All right, so a couple things just to point out. One, that these are functions of angles. So we're putting in an angle as the input. We're getting out a number as the output value for cosine and sine. All right, and those values are always going to be between -1 and 1, because if you're one of the points in the unit circle, your x-coordinate must be between -1 and 1, and so is your y-coordinate between -1 and 1. All right, the output range of tangent a little bit different. Okay, before we get into finishing this off, we're just going to review a little bit of what we've done so far. I want to take a moment and talk about the Pythagorean identity. All right, so we have our embedded right triangle in the picture here. The base side length is x, the height is y for that right angle triangle. And if we use the Pythagorean theorem, x squared plus y squared would then equal 1 squared. 1 squared is 1. But since x is cosine theta and y is sine theta, we're just going to substitute in cosine of theta for x and sine of theta for y into our expression here, or to our equation, excuse me. And that gives us the most fundamental of the trig facts, which is that the cosine of the angle theta squared plus sine of the angle theta squared, as long as the angle is the same, is going to have to add up to 1. All right, again, y coming straight from the definition. These are points on the unit circle. The x-coordinate and the y-coordinate are cosine and sine of that angle theta. All right, what we've done so far up to this point was to compute values for cosine and sine that were very simple. All right, ones where we know the points on the x-axis. So we started out with 0 and 90 and 180 and 270 and so on and so forth there, because we know that those coordinates are 1, 0, 0, 1, -1, 0, 0, -1. So cosine of 0 is, say, 1, and sine of 0 is 0, because that's where the terminal side of that angle hits the unit circle. All right, likewise for 90 degrees. If we draw the 90-degree angle, the terminal side of that angle intersects the unit circle at the point 0, 1. So cosine of 90 degrees is 0. Sine is 1. Similar for 180. We'll skip over that. If we go to 270, drawn in green, right, 3/4 of a revolution, the terminal side intersects the unit circle at the point 0, -1. So cosine of 270 is 0. Sine of 270 is -1. We can also think about this in radian mode. If we have cosine of 3 pi over 2 would be the same as cosine of 270, which would be 0, similar for sine. All right, what we also did in class was derive the coordinates of a 45-degree angle, derive the coordinates of where the terminal side of a 45-degree angle intersect the unit circle. All right, we did that using some symmetry. Along the line, the terminal side, that's the 45-degree line, that's the line y equals x. All right, the x-coordinate and the y-coordinate are the same. And therefore, sorry, I jumped there a little bit. When we go to use the Pythagorean theorem, we'd have normally x squared plus y squared equals 1, but we can put in here that x is equal to y, so we get x squared plus x squared equals 1, and that's an algebraic equation we can solve for x. Combine like terms, divide by 2, take the square root, and then we have the x coordinate of our point. All right, now we also rationalize the denominator, multiply the top and bottom by the square root of 2 to rewrite that as square root 2 over 2. sorry, it keeps jumping back to where I just was there. I don't know why. Sorry about that. Just trying to undo the highlighting there. All right. So what does that tell us then? All right. What does that tell us? Well, it tells us we know the points on, or sorry, we know the point where the terminal side of our angle, 45 degrees in this case, intersects the unit circle, and therefore we know the values of cosine and sine. Cosine of 45 degrees was square root 2 over 2. Sine is also square root 2 over 2. All right, so that's just kind of a quick recap from what we've done so far. All right, and it also told us we had a special triangle that we're going to use going forward, that if we have a 45, 45, 90, that the side lengths, or assuming we're talking about the hypotenuse having length 1, the other sides are square root 2 over 2 respectively. All right, and that will help us compute other values for sine and cosine. All right, now we're going to do a very similar thing for the 30, 60, 90 triangle. All right, so if we have a 30-degree angle, which I have drawn here, what our job is, if we're going to compute the outputs for cosine of 30 and sine of 30, we need to know where our angle intersects the unit circle. All right, so we're trying to figure out those coordinates for x and y. And we're going to be able to figure out those coordinates using some symmetry. All right, so what I've done down below here is redraw the 30, 60, 90 triangle in the first quadrant. Now, try to reflect that over the x-axis to redraw that triangle down below there. Sorry about that. Again, forgive me, it's jumping a little bit on me there. All right. So when we reflect that down, we end up getting that triangle down below the x-axis. Forgive me on that. All right, and what we want to look at now is that we have now an actual equilateral triangle. All right, so we've got these angles in the corners. I'm just going to go over those in green. We have a 60-degree angle in both these corners and this corner. So all the side lengths must be the same. Now, what is that? What do we know? We know this height is y, and therefore this height is also going to be y. If the hypotenuse for the original triangle we've drawn that is equal to 1, then this side length has also got to be 1 because it's an equilateral triangle. So y plus y is equal to 1, all right, which tells us 2y is equal to 1, which then tells us y must be 1/2 dividing both sides by 2. All right, so what we have there is the y coordinate. We know the y coordinate now. All right, and I'm going to just go through and look at the derivation for the x coordinate. You're going to see the result. I'll talk through the steps, but you will see the result when I scroll down, not the end of the world. All right, so looking at the left side of the screen, what do we know so far here? We know that the y coordinate is 1. All right, so what we're going to do is plug that in to the Pythagorean theorem, where we'd have x squared plus y squared would equal 1. Well, we'd be putting in 1/2 for y and 1 for the hypotenuse when we go down and do this below here. I'm just highlighting that in light blue. All right, now that when we do that, we put in 1 for C, and we put in y, or 1/2 for B, and then x for A, we get an algebraic equation. We can then solve for x. We square 1/2, we get 1/4. We square 1, we get 1. Now we subtract 1/4 from both sides. That's 4 over 4. All right, so what we're thinking about here is this is 1 over 1. Rewrite that by multiplying the top and bottom by 4. 4/4 minus 1/4 will give us 3/4. So we get x squared is equal to 3/4. We can take the square root, extract square roots to get that x is plus or minus the square root of 3 over 2. We're talking about a point in the first quadrant, so our x coordinate has to be positive. All right, so we're going to take the plus sign there, and that shows us that we now know both the x and y coordinates of where the terminal side intersects the unit circle for the 30-degree angle, and therefore we know the values for cosine and sine. of 30 degrees. They're square root 3 over 2 for cosine and 1/2 for sine. All right, now continuing on with our note packet, that also tells us we know a special triangle now, the 30, 60, 90, assuming the hypotenuse is length 1, we have across from the 30-degree angle is length 1/2, across from the 60-degree angle is square root 3 over 2. Again, we can think about these in terms of radians also, pi over 6 and pi over 3. All right, again, think about that. Across from the shorter side length, or sorry, across from the smaller angle, we must have the smaller number, right? And the square root of 3 over 2 is larger than 1/2 because the numerator is larger for the square root of 3 versus 1. All right, so keep that in mind here. All right, always we had the across from the 30-degree angles to 1/2, across from the 60-degree angles to square root 3 over 2. Now we can rotate that triangle around and get another known pair of values for cosine and sine by embedding, again, using the 60-degree angle and talking about our embedded right triangle we get by dropping the perpendicular down. I'm just going to highlight that quick, right? We always, from where the point where the terminal side of our angle intersects the unit circle, we drop the perpendicular down to create that right angle triangle. Now, across from the 60-degree angle, we have the square root of 3 over 2 as the height and 1/2 as the base length across from 30 degrees, and therefore our x-coordinate is 1/2 and square root 3 over 2 respectively there. All right, which again tells us we know some values for cosine and sine. Cosine is the x-coordinate, sine is the y-coordinate, so it's another pair of values that we know. All right, so again, some note here, we have that, right? We can do this because we can write down these side lengths using some symmetry, using the Pythagorean theorem, so we can compute these by hand for these special angles like 45 degrees for the 45-90 triangle and 30-60 with the 30-60-90 triangle. All right, so we have some values we've computed. Notice we've got for these acute angles, we've got the values for cosine and sine figured out. All right, and we can write them down in exact form. We can also compute these with a calculator to get the decimal equivalents if that is something that we would need. All right, now, again, I'm re-recording because I had something screw up, got messed up, all right, in my last recording. So we can use these results and these special triangles with reference angles to compute other values for cosine and sine. So, for instance, for 135 degrees, I've got that angle drawn here. 135 degrees is this angle with the terminal side drawn there. All right, now, if that's 135 degrees, then to figure out our reference angle right here between the terminal side and the x-axis, and that's always what the reference angle is, not between your terminal side and the y-axis, always the acute angle between your terminal side and the x-axis, we would simply figure out what is 180, which is a half a revolution, minus 135 to give us 45 is our reference angle. Well, that is therefore a 45-90, right? This length here, this radius of the unit circle is 1. So we know the side lengths are square root 2 over 2 and square root 2 over 2. The one thing we're doing a little bit different here, though, is we're adding this negative on the base length. All right, and lengths aren't negative, but for us using the definition for cosine and sine, it's going to be convenient for us to label that as a negative square root 2 over 2 because we're going left from the origin and then going up to get to our point in the second quadrant. So the x-coordinate is negative, the y-coordinate is positive. So our reference angle is 45 degrees. That helps us label the coordinates of the point where the terminal side of the angle intersects the unit circle. And we get negative square root 2 over 2 and positive square root 2 over 2. And that tells us our values for cosine and sine. And cosine is the x-coordinate, sine is the y-coordinate. And this works similar for other angles, all right, other common angles, all right, like 120 degrees, which I've got drawn and labeled down here. And let's just look at that. So these are some more values we can figure out. Again, the 120 degree angle is drawn here. 180 minus 120 gives us 60, so our reference angle is 60, right? And we have to just be careful here. Across from our reference angle is the square root 3 over 2. All right, across from the 60-degree angle is the square root of 3 over 2. Across from the 30-degree angle is 1/2. So we have to label that side length on the bottom negative 1/2. All right, which gives us the coordinates of our point, and therefore gives us the values for cosine and sine. All right, gives us the coordinates of the point where the terminal side of that angle intersects the unit circle is negative 1/2 square root 3 over 2, and therefore those are the values for cosine and sine respectively. And this is similar for other angles we have in our document. So for instance, 150 degrees, also over here in quadrant 2. We draw that angle. We want to know what are the coordinates of the point where that angle intersects the unit circle. Well, we got a 30-degree reference angle, so across from the 30-degree angle we have 1/2. Across from the 60 we would have square root 3 over 2, and we're counting that negative. All right, so our values for cosine and sine come out to negative square root 3 over 2 and positive 1/2. All right, and we can do the same thing for some of these other angles, like these special kind of angles that we're going to get a reference angle or reference triangle that has either a 45 or a 30, 60 or 30 or 60 degree angle in it. We can even use that to help us when we're doing negative angles. All right, so let's do a couple more. I think I'm going to do 225 and 300, and then we'll look at a homework question after that. So 225 degrees, again, drawn here. Let's go over the results. So now we've got a 225 degree angle, terminal side drawn there. We want to know the coordinates of the point where it intersects the unit circle. Well, we know our reference angle is 45 degrees because we're going to do 225 minus 180 to figure out how much past 180 we went here. All right, that's the acute angle between the terminal side and the x-axis, and that's a 45 degree angle. 180 or 225 minus 180 is 45. So we know the side lengths. They have to be square root 2 over 2 and square root 2 over 2. In this case, they're both coming out negative because we're going left and down. We're going in the negative x direction and the negative y direction. All right, again, labeling the, thinking about it that way helps us to label our points correctly, our point, excuse me, in the coordinates of that point to be negative square root 2 and negative square root 2 over 2. So our cosine values are of 225 and sine are both negative square root 2 over 2. Similar for 300. All right, if we look at the 300 degree angle drawn here, so terminal side on the, or initial side on the x-axis, we would go 300 degrees. 360 minus 300 is 60, which shows us that our reference angle, all right, the acute angle between the terminal side and the x-axis is 60, and therefore we can label across from the 60 degree angle, in this case negative square root 3 over 2, across from the 30 degree angle, positive 1/2. Okay, why? Because we're going right and then down. So x is positive, y is negative. So we can therefore label the point, it's done below here, 1/2, positive 1/2, negative square root 3 over 2, and therefore we know the values for cosine and sine based off the definition. Okay, last one are with this group here. What about negative 225? So in this case, remember, we draw negative angles. We go from the x-axis clockwise, not counterclockwise. Counterclockwise is for positive angles. So a negative angle, we have it as terminal side land here. Now, that also shows us our reference angle is, once again, 45 degrees. And the acute angle between the terminal side and the x-axis is 45 degrees. Well, if we have a 45, 45, 90 right triangle, we know how to label that, assuming the length on the hypotenuse is 1. Oops, sorry, I jumped a little bit there. So we know the side lengths are negative square root 2 over 2 because we're going left, positive square root 2 over 2 because we're going then up, and therefore we know the coordinates of the point where our terminal side intersects the unit circle are negative square root 2 over 2 and positive square root 2 over 2. What I wrote in blue here was just emphasizing that these angles are coterminal. All right, so the angle negative 225, which we would get by going clockwise, is coterminal to 135 degrees, positive 135 degrees, but they have the same, since they have the same terminal side, they have the same point on the unit circle where they intersect that terminal side, and therefore their values for cosine and for sine are the same. So for coterminal angles, they're going to have the exact same output values for cosine and for sine. All right. Now, the last thing we're going to do is look at a problem from the homework. All right, and we'll get to that, but it goes based off of this little remark we have in this bullet that we can only compute the values for cosine and sine by hand if it's a special angle, so like 30, 60, 90, or if that's one of our reference angles, or 30, 60, 90, or 45. If it's a point we know the coordinates of where our terminal side intersects the unit circle, or maybe we're given the point on the unit circle, then we can just read them off. Other than that, if we're either given one of cosine or sine of the angle, then we'll be able to figure out the other one using the Pythagorean identity. And that's what we're going to do in the last example. All right, so we're going to get to that problem in a moment here, okay, which is going to be number 12 from the homework. I'm just going to open up homework 7.3 quickly. All right, I think I'm re-recording this, so it's probably going to show this as correct. All right, so but what's it giving us? It's saying if sine of the angle theta is negative 1/4, then what is the value for cosine of that angle? So what we want to do in here is figure out that value. Again, we don't even know what the angle is. We're just figuring out the value for cosine, knowing the value for sine. All right, let's see how the details of that work out. Okay, so here's what we're going to do. We're going to figure that out, all right? And we'll come back to this. Let's just do this first, and then we'll look at the breakdown of the problem. All right, we'll use this here. So let's talk about this sign convention here, the algebraic sign. In quadrant 1, both coordinates have to be positive, right? Because we're going right and then up. In quadrant 2, both we're going left and then up, so cosine is going to be negative because that's the x-coordinate, sine is going to be positive. If we're going to quadrant, if our angle is in quadrant 3, then we're going left and then down, and therefore both cosine and sine are going to be negative. If we're in quadrant 4, we're going to be going right and then down, and therefore, jumped a little bit, and therefore cosine will be positive, sine will be negative. All right, so how do we answer this question here? What we're going to do is use the Pythagorean identity. So you can use the x squared plus y squared is equal to 1 and think about, well, sine is equal to y. That's fine. Or we can use the equivalent Pythagorean identity, which says that cosine of theta squared plus sine of theta squared is equal 1. All right, and when we do that, what we want to think about doing here is replacing cosine, or sorry, in this case, we're given sine was equal to negative 1/4. We're going to find cosine, so we're going to put in open parentheses because that really stands for sine of the angle theta, then squared. It's written this way with the square on top of the sine, S-I-N part. That's just to make it less to write. It really means sine of theta in parentheses squared, but it's just quicker to write that. So now we're going to plug in the negative 1/4 there and then algebraically solve this equation for cosine. So we square the 1/4, which gives us 1/16. Then we're going to solve for cosine, subtract the 1/16 from both sides, right? Rewrite 1 on the right side as 16 over 16. 16/16 minus 1/16 will give us 15/16. So now we have cosine of theta squared is equal 15 over 16. And then we're going to get the square off by extracting square roots. All right, in this step here, we've taken the square root of the top divided by the square root of the bottom, which gives us square root of 15 divided by square root of 16, which is 4. Got to leave the square root of 15 on there. All right, now which one of these do we choose? Do we choose the negative or the positive? In this case, we're talking about an angle in quadrant 3, and therefore cosine and sine are both negative. So in this case, we want to choose the negative. All right, so in this case, for this problem, we would get cosine of theta is equal to this negative square root of 15 over 4. So once again, this problem can be answered without actually knowing what the angle theta is. Right? We knew half of the ordered pair where the terminal side intersects the unit circle. We could find the other half using the Pythagorean identity. All right, that's it for this recording.